Hi everyone, my name is Caroline Variath. I am from the Faculty of Nursing at the Hamburg School of Health Sciences, and today we're going to talk about ABG analysis. So the learning objective of this video is for us to be able to analyze an arterial blood gas result and also to evaluate the changes that may reflect those blood gas results on our client. So let's get started. The first step in analyzing an arterial blood gas result is to look at the normal values that actually affect the arterial blood gas. So let's start off with the pH. What is the normal value of a pH? And most of us know that is 7.35 to 7.45. While we know that is what the normal is, what does that actually mean? So the pH represents the acidity or alkalinity of our blood. And that is kind of represented by the presence of hydrogen ions in our blood. So the greater the hydrogen ion, the more acidic our blood is. And that's actually reflected in the pH as a negative, by a negative algorithm. So if the blood is acidic and the hydrogen ions are higher, it's represented by a lower pH. So the pH will be less than 7.35. What if the blood has less hydrogen ions, which is the acidity of the blood? If that's less, that's represented by a higher pH value, which is greater than 7.45. Okay, so that's step number one. What is the pH of our blood? So if we know it's less than 7.35, we know it's acidic. If it's greater than 7.45, it's basic or alkaline. So now we're going to think about what is actually causing our blood to be acidic or alkaline. And there are some factors that play into this, and some factors actually make the pH go one way or the other. And the first one of those factors is PCO2. And that's the level of carbon dioxide in our blood. In our arterial blood. So carbon dioxide, what is the normal value of carbon dioxide? It's 35 mmHg to 45 mmHg. So what exactly does that mean? What does that mean? Why does carbon dioxide affect the pH of the blood? Now, when carbon dioxide combines with water in our blood, then that results in the production of carbonic acid. This is how I'd like to remember. So carbon dioxide combines with water to produce carbonic acid. It's an acid. Therefore, the higher the PCO2, the carbon dioxide in our blood, there will be a higher number of hydrogen ions, or the acidity of the blood will be higher. And therefore, if the carbon dioxide is low, we have less hydrogen ions. And therefore, our blood will then be alkaline, and they'll be represented by a pH that's higher than 7.45. And then, so this factor, carbon dioxide, what system controls that? And that would represent or reflect the respiratory system. Okay? So yes, that's one element that kind of determines what our pH is. And the next element that determines our pH is bicarb. So bicarb, how does that, let's start with what's normal bicarb. So normal bicarb is 21 millimole per liter to 28 millimole per liter. And this number might differ a little bit in different institutions. But for the most part, it's 21 to 28 millimole per liter. What is bicarb, and how does that affect the pH? So what happens with bicarb is that bicarb attaches with the hydrogen ion. It attaches with the hydrogen ion, and it excreted by the urine. So the acidity that's created by as a byproduct of metabolism, the bicarb acts as a buffer to attach to it and try and get rid of it. So if there is less buffer, less bicarb, then there's not enough to get rid of the hydrogen ion. Therefore, the blood will then, if bicarb is less than 21, then that would mean that the pH will be acidic. Similarly, if there's an abundance of bicarb, which is 28 or higher than 28, then it gets rid of more and more of the acidity of our blood. So the hydrogen ions will be low, right? And therefore, that will lead to an alkaline state of the blood. So the pH will be greater than 7.45. And which system represents the buffer? So the a bicarb is actually reabsorbed or even produced by the kidneys and gets rid of that acidity caused by metabolism. So this represents the metabolic side of things. So these are the two factors that play a role in maintaining the pH. And as we do problems, as we go along, we'll figure out how each of them affects our pH. Now, in an arterial blood gas, you will also see PO2 levels, which represents the oxygenation, and also base excess, which it kind of reflects also how much bicarb there is to keep the stability of the pH. But for our purposes, for the analysis purposes, we're just going to look at the pH, PCO2, and HCO3. So we're going to move on now and work through some problems, and all of this will come to light. I know this looks a lot confusing, but we're going to try and figure this out together, okay? Okay, so we talked about what the first step of analyzing an arterial blood gas result was, and that's to know what the normal values are. And in order to understand how that reflects on the client, you also need to know what those meant. And on top of that, I'm also going to talk about knowing when a pH becomes acidic and when a pH becomes alkaline. So 7.35 to 7.45 is the normal pH value. And remember, pH reflects the number of hydrogen ions in the blood, and the more the hydrogen ion, the more acidic the blood is. And that's reflected using a negative algorithm. So the more the hydrogen ions, the less the pH. So it will be less than 7.35, making the blood acidic. And then if the hydrogen ions or the acids in the blood is less for some reason, then that will be reflected by a higher pH level, greater than 7.45, making the blood more alkaline. And what are the components that makes the blood acidic or alkaline, or keeps it normal? And those are the two systems that help maintain that acid-base balance. And the first one we're going to look at is the respiratory component, which is the carbon dioxide. So remember, carbon dioxide mixes with water and produces carbonic acid, which is the same as having a lot of hydrogen ions. Therefore, the higher the carbon dioxide, the more acidic the blood's going to be. And then the lower the carbon dioxide, the more alkaline the blood's going to be. And just think of some conditions where the client's carbon dioxide is going to be more when they are actually retaining it in their circulatory system instead of expelling it. So what causes or what makes them retain all of that carbon dioxide in the blood? Or what's making them blow it out? If it's alkalosis, or if it's less than 35, what's making them blow out a lot of carbon dioxide? When do we see them actually have less amount of carbon dioxide in the blood? And then the last component that affects, or second component that affects the pH, is the metabolic component. And that's represented by bicarbonate. And bicarbonate, like I said before, is regulated or produced by the kidneys. It's reabsorbed by the kidneys, and also the kidneys produce bicarbonates of its own. So what does bicarbonates do? It attaches itself to the acids and gets rid of them. So if the bicarbonate levels are low, there's not enough to get rid of the acids. Therefore, the blood has more acid in them, making it acidemic. And then if the bicarbonates are in abundance, so the buffers are in abundance, then it attaches to all of that hydrogen ions and gets rid of them, so making the hydrogen ions less, or the acid component less, making the blood more alkaline. So think about some conditions in a client that would make either of these happen. So for example, if the kidneys are not able to reabsorb that bicarbonate, or if the kidneys are not functioning they normally would, and they're not producing enough bicarbonate, that would lead to a lower bicarbonate level. Or if there's more acid being produced by the body and the kidney cannot keep up with that production by producing more bicarbonate, that would also lead to a change in these numbers. Or if the kidney has abundance of the bicarbonate and the body does not have as much acid in it, then it would go the other way. So just thinking about some of those concepts is a good idea. And we'll talk about conditions like that as we go through our examples. So now let's look at how to actually analyze a blood gas result. I've written out 2 examples here, and I've also drawn a little box. So this box allows us to kind of visualize where things go and kind of put together what's going on with that arterial blood gas result. I'll talk about it as we work through these examples. So in the first example, we're going to go ahead and analyze that blood gas result. So the first step in analysis is to look at what's going on with the pH of the blood. We've got to figure out what's going on with the pH of the blood. Is it normal? Is it high or is it low? Is it high or is it low? We've got to figure that out in order to figure out what's going on with the client. So pH in this example is 7.32. 7.32 is less than 7.35, making the blood acidic. So pH in this example is acidic. Okay, so now that we know that the pH is acidic, we've got to figure out what component, is it the metabolic component or the respiratory component that is causing the pH to be acidic. And how do we do that? Well, let's analyze them as well. So step 2 is to analyze the carbon dioxide in the blood, in the arterial blood. So carbon dioxide level is 37. 37 falls between 35 and 45, which is the normal range. Therefore, the PCO2 or the carbon dioxide is normal. Yes? Okay, so we still haven't figured out what's causing the acidosis. So one of these elements also have to be acidic for the pH to be acidic. So we haven't figured out what's causing the acidemia yet. So now let's look at the final component of this, and that's a bicarbonate. Bicarbonate is 18. So 18 is less than 21, which makes the blood acid or acidemia. So blood is acidemic because of that low bicarbonate level. So bicarbonate, CO3, is also acidic. Therefore, we know the pH is acidotic, and now we know what the causative factor is. What's causing that pH to be acidotic? So this example is acidosis, and it's caused by the metabolic component. So it's metabolic acidosis. This client is actually admitted with diabetic ketoacidosis. So there's a lot of acid in the bloodstream, and the kidneys are not able to produce enough buffers to get rid of it. Therefore, the acidemia. Okay, so it's gotten rid of a whole lot of the acid, therefore the kidneys have lost quite a bit of buffers, and it can't replenish it at the rate it's losing it, and that's why we're in acidosis. Okay, so now let's look at the next example. So this, as you can see, kind of tells you where things lie. So it's almost like a tic-tac-toe box, where if it's acidosis, you can look at the pH and the HCO3. They're all lining up together, which means that is the right answer. So pH is acidotic and is caused by a metabolic component. This is great. You can use this in a normal blood gas setting, but this box, if it's a more advanced, or if the blood gas result's a little bit more complicated, it doesn't work the tic-tac-toe way, but it actually gives you a good visual component as to just look at the box and kind of figure out where everything is, and kind of figure out what the blood gas actually reflects. Okay, so example 2. So let's break it down. First, we need to know if there's anything wrong with the pH. The pH is 7.50. 7.50, what does that mean? It is greater than 7.45, which means there's less amount of acid in this client's blood. Therefore, we're in alkalosis. Okay, so this pH is alkaline. Okay, so pH is alkalosis. Okay, so what's my next thought? Okay, pH is alkalotic. I want to know what's causing my client's pH to be alkalotic, because if I just have this information, I don't know enough about my client, right? It doesn't really reflect what might be going on with my client. So the two components that could be causing the pH to be alkaline, I'm going to assess those two. So first off, out of the two would be the PCO2, which is the carbon dioxide. PCO2 is 32. 32 is less than 35. Less than 35, which means carbon dioxide, there's less amount of carbon dioxide in our body. Therefore, there's less carbonic acid, and therefore there's less acidity, and so therefore the blood is more alkaline. I hope we're following all of those things that I'm just saying. Good. Okay, so PCO2 is 32, which is less than 35, making it also alkaline. Okay, and step 3 is bicarb. Bicarb is 22. Normal bicarbonate is 21 to 28, so it's within the normal level. So HCO3 is normal. So if those of you play tic-tac-toe, you know what lines up. pH is alkalotic, and PCO2 is also alkalotic. So we know that the blood is in alkalosis, and we know what's causing it. It is the respiratory component. Right. So when you think about this client, the PCO2 is 32. How might that reflect on the client? So 32 meaning they're not retaining adequate amount of carbon dioxide, so blowing out carbon dioxide. So you might see that as increased respiratory rate or hyperventilation. This client actually might be hyperventilating. So this was a client who came in straight after an exercise, and they were working harder than they normally do, and they were blowing out too much carbon dioxide. Okay. So let's look at one more example of arterial blood gas, and we'll analyze them together. So this client is now come to the hospital, and he has COPD exacerbation, and they said, okay, let's do an arterial blood gas to see what our pH and the values look, or acid-base balance looks like. So the pH of this particular client is 7.28, and PCO2 is 55. HCO3 is 26. Okay, so remember, this client has come in with COPD, and we've done a blood gas, and this is what the values look like. So we've got the arterial blood gas values. Now we've got to analyze it. Okay, so first step in analysis, we know, is to look at the pH, because we need to know what state the blood is in. So pH is 7.28. 7.28 is less than 7.35, making it acidic. So pH is acidic, right? So now we want to know what's causing this acidemia, and if we know our pathophysiology and this patient's come in with COPD, we kind of know it's already which direction we're going, right? So let's look at the carbon dioxide next. Okay, carbon dioxide is 55. 55 is greater than 45, meaning the carbon dioxide is also in the acidic state. So it's lots of carbon dioxide in the blood, more than there should be. Therefore, there's more carbonic acid, which is equal to having a lot more like hydrogen ions, and therefore making the blood acidic. So pH of the blood is acidic because of the PCO2 being acidic also. And third and finally, we're also going to look at, just because we have these two doesn't mean we're not going to look at the bicarbonate. So bicarbonate is 26. 26 is between 21 and 28, meaning it is in the normal range. So we can say that this client is in acidosis, and we know it's caused by a high PCO2 level or high carbon dioxide level, making it a respiratory acidosis. So if you think about the pathophysiology of this client who's just come in with COPD, they've got bronchoconstriction, they're not ventilating the way they should, so they're not able to blow out or get rid of that carbon dioxide as you and I would be able to. So therefore, it's accumulating in that client's blood, and that's reflected. So when that goes up, it also creates a higher amount of hydrogen ion in the blood, therefore making the pH also acidemic. Now, so this is how you would analyze a basic arterial blood gas result. So now we're going to move on to think about, if this client comes to you, is this client going to stay in this state, or is the pH going to stay in this state? You and I know that our body always tries to maintain a homeostatic state. And how does it do that? By trying to compensate for something that's happening in the body itself. And so in the next video, we're going to talk about how pH or a blood gas results look like when there's partial or full compensation, and also if there's mixed acid-base issues within a client as well. Thank you.